Hello and welcome back to Chapter 3, Part 2. Last time we talked about the electromagnetic spectrum, which is the whole range of electromagnetic radiation or light. Now, if you look through a spectrum, you would use a device called a spectrometer, and what you will end up seeing is a continuing band of colors that looks just like the figure over there. Now, the curves that you see right there are graphs of the spectrum's intensity. So think of intensity as how bright something is versus the wavelength in this case, but it could be versus the frequency. Now you will see lots of these vertical color bands in your reading. Try to think of them in terms of intensity versus wavelength or frequency. If you look closely at the stars in the constellation Orion, which is depicted in the picture right here, and another name for Orion is M42, you will notice that the stars there are not all the same color. One of those stars, the one on the upper left, is called Betelgeuse, and it is quite red. On the other hand, Rigel, which is on the lower right corner, is blue. Now, these differences in color arise from differences in temperature. The starlight that you see comes from gases that make up the visible surface of the star, which is called the photosphere. Now, the photosphere is the visible surface of a star because it is dense enough to emit lots of light, but transparent enough to allow that light to escape. Now, why do stars produce light? Well, for the same reason a heated horseshoe, for example, will glow in a blacksmith's forge. So it is because they're hot. So stars produce their light because they're hot. The light from stars or from a glowing horseshoe is produced by the acceleration of charged particles. Now, usually the accelerated particles are electrons because they are the least massive charged particles and they are on the outsides of atoms, so they are the easiest to get moving. An electron is surrounded by an electric field. And if you disturb an electron, the change in its electric field spreads outward at the speed of light as electromagnetic radiation. Now, we talked earlier in Chapter 2 about acceleration, defined as the change in velocity of an object, or the change in motion. So, whenever you change the motion of an electron or some other charged particle, you generate electromagnetic waves, or radiation. Think of, for example, if you run a comb through your hair, you disturb electrons in both the hair and the comb, which produces static electricity. That produces EM radiation, which you can hear as snaps and crackles. Now, the same thing happens with the stars. Stars are hot, and they're made up of ionized gases, so there are plenty of electrons zipping around. The molecules and atoms in any object, not just stars, but any object, are in constant motion. And in a hot object, they're more agitated than in a cool object. So you can think of this agitation as thermal energy. So if you touch an object that contains lots of thermal energy, it will feel hot as the thermal energy flows from that object into your fingers. This flow of thermal energy is called heat. On the other hand, temperature is the average speed of the particles. So hot cheese and hot green beans can have the same temperature, but the cheese can contain more thermal energy and can burn your tongue. So heat refers to the flow of thermal energy, and temperature refers to the intensity of the agitation among the particles. So when astronomers refer to the temperature of a star, they're talking about the temperature of the gases in the photosphere. And if you remember from the last lecture, they express those temperatures on the Kelvin temperature scale. So keep in mind that differences in color when you look at the stars arise from differences in temperature, and those temperatures are going to be measured in degrees Kelvin. Now, I talked a little bit about thermal radiation, and that's very important. So the radiation emitted by a heated object is given the special name, and it's called blackbody radiation. Now, a perfectly opaque object would be both a perfect emitter and a perfect absorber of radiation. At room temperature, such a perfect absorber and emitter would look black, but at higher temperatures, it would glow at wavelengths visible to human eye. Now, many objects in the sky, including the sun and stars, primarily emit blackbody radiation because they're mostly opaque. Hot objects emit blackbody radiation, but so do cold objects. Ice cubes are cold, but their temperature is higher than absolute zero, so they contain some thermal energy and must emit some blackbody radiation. The coldest gas drifting in space has a temperature only a few degrees above absolute zero, just like we said in the last lecture, but it too emits blackbody radiation. And if you take a look at the picture right here, that's a graph of the blackbody spectrum, which is a simplified mathematical model for the continuous spectra of ideal objects that only depend on the object's temperature. So notice how this is a graph of intensity versus frequency or wavelength, and it has this shape, and all blackbody radiation has that exact same shape. And notice how the arrow is pointing at the peak. So that would be the peak wavelength. Which brings me to two radiation laws. The first one is called Wien's law. This law says that the peak wavelength, or another way of putting it is the maximum wavelength, is inversely proportional to temperature. Notice how if you look on the x-axis towards the left, the wavelength is increasing. If you look towards the right, the frequency is increasing. So as the wavelength is increasing, what happens to the temperature? Well, the temperature, according to this graph, will be decreasing. So the mathematical relationship looks like this. The maximum wavelength is approximately equal to 2.9 millimeters. Milli is 10 to the minus 3. So millimeters divided by the temperature Kelvin. So this is a blackbody, or another way of saying this, a Planck curve, and it represents the intensity of radiation emitted by an object. Now, right here in this example, we have several curves. We have 4 curves corresponding to temperatures of 300 Kelvin is the smallest one, and that represents room temperature. 1000 Kelvin is where the object is beginning to glow dull red when it's heated up. At 4000 Kelvin, it will look very red hot, and 7000 Kelvin, it will look white hot. Now notice how the blackbody curve has the same shape, but what it's doing is it's shifting towards the right. So as you can see, the peak wavelength is changing because it's falling at a different part of the wavelength part of the spectrum. So notice how as temperature changes, so does the maximum wavelength. So the peak of the blackbody spectrum shifts towards shorter wavelengths or higher frequencies when the temperature increases. Now this is very important in astronomy because this is telling us that we can get an object's surface temperature from its spectrum. So by looking at the stars out there and looking at them through a spectrometer, we can analyze the spectrum and get the object's temperature without ever going anywhere near it with a thermometer. So that's very important. So this is the first law. The second law I would like you guys to learn is called the Stefan-Boltzmann Law. What this law tells us is that the total energy per unit area emitted is proportional to the fourth power of temperature. So let's write this mathematically. So F, which in this case represents not a force, but the total energy per unit area, is equal to sigma. Sigma, guys, is just a constant, and it's called the Boltzmann constant, and I'll tell you in a minute what its value is, times T. Capital T, do not confuse with lowercase t. Lowercase t is time. Capital T is the symbol for temperature, and it's measured in degrees Kelvin. So F is equal to sigma T to the fourth. So what does this formula tell us? It tells us that the hotter an object is, the more energy it's going to emit. So if you make an object just a little bit hotter, and it will get a lot brighter per unit area. Not 4 times brighter, but T to the fourth times brighter. Now a little bit about the units. If F, or you may see this as the symbol of E for energy, so energy per unit area is power per unit area, and the units used for that is watts per meter squared. Temperature again is in Kelvin, and the constant sigma, you can look it up in the back of your book, or here it is right here, is 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the fourth. Now, if you look at this right here, actually, let's move on to the next slide. Here's the illustration of Wien's law, and Stefan-Boltzmann law. So what is this actually telling us? Well, the hotter object emits more blue light. How do I know that? Because if I look at the curve that represents 12,000 Kelvin, so the highest bumped blackbody curve, notice how the object has more purple, okay, or blue light being emitted than red light. And then if I look at an object, let's look at the lowest curve that represents a 3000 Kelvin object. Notice how there's more red light being emitted. So the hotter object emits more blue light than red, and therefore looks blue to our eyes. And the cooler object emits more red than blue, and consequently looks more red. So now you can understand why Betelgeuse and Rigel have such different colors. Betelgeuse is cool, and therefore it looks red, and Rigel is hot, and therefore it looks blue. So you can see that represented on the Planck body curve. Cool objects in general don't glow at visible wavelengths, but still produce blackbody radiation. For example, the human body has a temperature of 310 Kelvin and emits blackbody radiation mostly in the infrared part of the spectrum. So infrared security cameras can detect burglars by the radiation they emit, and mosquitoes can track you down in total darkness by homing in on your infrared radiation. So although we emit lots of infrared radiation, we rarely emit higher energy photons, and we almost never emit an X-ray or gamma ray photon. So our wavelength of maximum intensity, our peak wavelength, lies in the infrared part of the spectrum. So let's put that in perspective with astronomical objects. So here's a nice picture from your book. It's figure 311, and it's a sample astronomical thermometer. So we're going to compare the black body spectra, the black body curve, at the temperatures of these 4 astronomical objects. So let's start with the one on the top, frame A. If you take a look at the Planck body curve, it says temperature is equal to 60 Kelvin. So that's very, very cold. And this picture is taken, if you notice on the lower left, at the radio wavelengths. And what it's showing is a cool, dark galactic gas cloud, which is called Bernard 68. At this temperature, it mostly emits radio radiation, as you can see from the shift on the Planck curve. And the peak wavelength is as 48 micrometers. If we look at frame B, and the temperature is 600 Kelvin, so notice how the Planck curve has shifted and the maximum peak wavelength has decreased. It went from 48 to 4.8 micrometers. So in this picture, we're seeing a young star, and this particular one is called Herbig-Haro 46. Now, the star's atmosphere peaks at 600 Kelvin, which means it radiates mainly in the infrared, which is why the picture wavelength on the bottom is highlighted as I, corresponding to infrared. Now in frame C, we have our own sun, and its peak temperature, we have a 6,000 Kelvin, and its peak wavelength has shifted down to 480 nanometers. And this is, remember, we're talking about the surface of the object, and the sun's surface is approximately 6,000 Kelvin. So it is brightest in the visible spectrum of the EM spectrum, of the EM radiation. How do I know that's visible? Because remember, the visible light is between 400 and 700 nanometers. So see how that peak wavelength of 480 falls within that range. And frame D is showing another object, and notice how its peak, it has 48 nanometers, so even less. Its temperature is 60,000 Kelvin, and this what this represents is a star cluster. This particular one is called Messier 2, and its temperature is 60,000 Kelvin, and this is a picture taken by an orbiting telescope. And you know it would have to be an orbiting telescope, meaning it's a telescope outside of Earth's atmosphere, because it's taking this picture in the ultraviolet. And remember, there's only 2 windows on the Earth's surface, which is the radio and the visible. So in this case, we have the ultraviolet. So black bodies are very important. So the black body curves that have to do with the temperature, the surface temperature of the object, because they give us a simple way to estimate the temperatures of things based on their spectrum. Now notice how the coolest object is 60 degrees Kelvin, and we talked about the dark galactic gas cloud. And the hottest is 10 times hotter than the sun's surface. So just take a look at these graphs, understand how the black body curve is shifting towards the right as the temperature is increasing. As that is taking place, the maximum wavelength is decreasing. So now I would like to talk a little bit about the Doppler effect. You may or may not have heard of the Doppler effect, and it's something very, very useful. Oops, excuse me about that. All right, so surprisingly, one of the pieces of information hidden in a spectrum is the velocity of the light source, what is emitting the light. Now, astronomers can measure the wavelengths of the lines in a star spectrum and find the velocity of the star. So the Doppler effect is the apparent change in the wavelength of radiation caused by the motion of the source or the observer. When astronomers talk about the Doppler effect, they're talking about a shift in the wavelength of EM radiation. But the Doppler shift can occur in any form of wave phenomena, including sound waves. Now, imagine a rocket ship launched from Earth with enough fuel to allow it to accelerate to speeds approaching that of light. Think of spaceships in Star Trek or something like that. Now, as the ship's speed is increasing, an amazing thing is happening. If you're on that spaceship, you would notice that the light from the star system toward which you're headed seems to be getting bluer. In fact, all stars in front of this ship would appear bluer than normal. And the greater the ship's speed, the greater the color change would be. Now, stars behind the vessel would seem redder than normal, but stars to either side would be unchanged in appearance. As the spacecraft slows down and eventually comes to rest relative to the Earth, all stars would resume their usual appearance. So the Doppler effect is this shift in the wavelengths. When a source is coming closer to us, or we're coming closer to a source, then we say we have a blue shift. If we're moving away from a light source, or the light source itself is moving away from us, then we say that we have a red shift. Now, I want you to keep in mind that this Doppler effect only takes place along the direction of motion, which is what we call the radial motion, the part of the motion that's towards or away along the line of sight, which is why in this picture, the stars that are perpendicular to the spaceship, so the ones that are on top and the bottom of the space shuttle, they appear normal because they're perpendicular to the direction of motion. But the stars in front and on the back, they're the ones that appear bluer and redder respectively. So the Doppler effect involves only the radial component of motion. So please keep that in mind. Now we can use this shift in wavelength, this shift in spectrum, to get the object's radial velocity. So we can figure out how fast a star is moving away from us or towards us. And we use that to figure out the speeds of any cosmic objects, not just stars, but galaxies too. So the Doppler effect is very, very useful in astronomy. And here is how we actually figure it out. The apparent wavelength, and when we talk about apparent wavelengths, it's the same idea as when we talk about apparent motion. So it's not the real wavelength, it's what the wavelength looks like it is. So you know how it's shifting, right? So it looks to be different than what it really is. So that is the apparent wavelength. If we divide that by the true wavelength, the real wavelength, then we know that that's going to be equal to the true frequency of the light source divided by the apparent frequency. And mathematically, this can be rewritten also in terms of velocity. So this is equal to 1 plus recession velocity, recession meaning how it's moving away from us. So recession velocity is the velocity of an object that's moving away from us divided by the wave speed. And guess what that wave speed would be? Well, since we're talking about light, that would be the speed of light. So let's rewrite this formula in terms of symbol. So the apparent wavelength, apparent lambda, divided by true lambda is equal to 1 plus or minus V over C. Now you may wonder, what is this plus or minus? Well, you use a plus if the object is moving away from us, meaning we have the recession velocity, which means that the light is redshifted, gets longer because it's moving away from us. And you use negative minus if the object is moving towards us, which means that its wavelength is blue shifted. It gets shorter. So let's take a look at this diagram right here. So remember, the Doppler effect depends on the relative motion of source and observer. Now, I want you to understand that it could be either or both objects moving. So it could be the source that's moving, it could be the observer that's moving, it could be both that are moving. So if we look at frame A, we have, let's say that object that emits light right there is a star. So if that star is not moving, it's emitting light in all directions, and we're observing that light, and we see its true wavelength because neither the star or the space shuttle are moving. Now let's say that the star is moving towards the right. So notice how the crest of the waves look like they're getting closer towards the right and further apart towards the left. So if you have an observer in a space shuttle on the right, picture these wavelengths getting crunched closer and closer together, getting smaller and smaller. So they're getting smaller, so they're blue shifted. So the observer on the shuttle on the right is going to see a blue shift of the true wavelength source. However, an observer behind the star, because the star is moving away from them, it's going to see a red shift. It's going to see an elongation, a stretching out of the true wavelengths of this source of light. So let's do an example. Let's say you have a source of light that's moving with a speed of 30 kilometers per second. What is its Doppler shift? In order to figure out, you can use the formula I gave you in the previous slide. So if you put that together, you can do the change in wavelength divided by the true wavelength is equal to the recession speed, which we know is 30 kilometers per second because they told us that, divided by the wave speed, which is always 300,000 kilometers per second. And we see that the Doppler shift, so the change in the wavelength, is going to be 0.01%. So here is a more down-to-earth application, which you may or may not have experienced. So in this picture, we see the police radar measures speed by means of the Doppler effect. So that's what radar guns that are used to clock the speed of a pitcher's fastball would do, for example. And there's several other applications for this. Now in this case, the reflected radiation, which is represented by the blue crests, and they're reflected back from the oncoming car, they're shifted to shorter wavelengths by an amount proportional to the car's speed. So the policeman is going to use that to see how fast the car is moving, which could be above the speed limit. Now, for most of the objects in the universe, this relative shift is so tiny that we can't detect it using the shift of the whole continuous spectrum. So what do? Well, we use places in the spectrum whose wavelength is precisely known by the presence of spectral lines, and that's how we figure things out. Now that's the subject of chapter 4. Now, a little bit of a summary of what we talked about in Chapter 3. We defined waves, and we talked about the period, the wavelength, the amplitude, and the frequency of a wave. We talked about electromagnetic waves as being created by accelerating charges. And the visible spectrum is the wavelengths of light that our human eyes can process, which is in the range of 400 and 700 nanometers. Now, the entire electromagnetic spectrum, starting from the largest wavelength, is radio waves, infrared, visible light, UV, ultraviolet, X-rays, and gamma rays. So that's something you should definitely learn. Now, we can tell the temperature of an object by measuring its black body radiation, and we can do that using Wien's law. We also have the Stefan-Boltzmann Law, which is very important because it gives us the energy per unit area that's emitted by an object. And then we talked about the Doppler effect, which can change the perceived frequency or wavelength of the radiation. And it depends on the relative speed of the source and the observer. If neither of them are moving, we're not going to see a Doppler effect. If either or both are moving, then we will see a Doppler effect. If something is moving towards us, it's going to be blue shifted, whereas if something is moving away from us, it's going to be red shifted. So please study chapter 3.4 through 3.5. Review the two radiation laws and the Doppler effect.